Hello geometry students, my name is Emigh, and this video is our discussion on sections 2.4 and 2.5, biconditional statements and definitions, as well as deductive reasoning. A biconditional statement is equivalent to writing a conditional statement and writing its converse. For a biconditional statement, we use the phrase if and only if. Or sometimes you'll see IFF like that. Looks like a typo, but it stands for if and only if. Now the notation for a biconditional statement has an arrow going in each direction. That's because your hypothesis, let's call it P, and your conclusion, let's call it Q. Before we were saying P implies Q. And we know the converse would be that Q implies P. But the biconditional statement says put these together, P implies Q and Q implies P. So shorthand to denote that, you'll see the double arrow like that there. All right, let's try an example. Write the following conditional statement as a biconditional. If two angles are supplementary, then the sum of their measures is 180 degrees. Okay, let's check. If two angles are supplementary, that means they add up to 180, then their sum of their measures is 180. That is true. And if we read it the other direction, if the sum of two angles measures is 180, then the two angles are supplementary. Okay, so this is true whether you read it if this, then this, or if you read it the other way, if this one, then this one, which is called the converse. So it's true either way, which means we're allowed to write it as a biconditional statement. It's actually really simple. You just cross out the then, cross out the if, and you just write if and only if in the middle. That's really it. So two angles are supplementary if and only if the sum of their measures is 180 degrees. Okay, a note. If the original statement is true and its converse, if the sum of the measure of two angles is 180, then the angles are supplementary, is also true, then the biconditional statement, so this one now has an overall truth value of true. Okay, and that is because this statement here was true when we read it P implies Q, and it was true when we read it Q implies P. Next example, write the statement as a biconditional. Is the biconditional true or false? And if false, we always want to remember to give a counterexample. If a closed figure is a triangle, then it has three sides. Okay, so we have an if-then statement. That's called a conditional statement. This right here after the word if is called our hypothesis. This right here after the word then is called our conclusion. Okay, if we read this, P implies Q, our truth value, if a closed figure is a triangle, then it has three sides. Our truth value is true. So P implies Q, truth value of true. Now let's read it the other way. Let's read it Q implies P. If a closed figure has three sides, then it is a triangle. Closed figure has three sides, it is true. That is also true. So truth value, true. Okay. A closed figure has three sides if and only if it is a triangle, would then be the biconditional statement. So it's not too bad. Just cross out the word if, cross out the word then, and like I said, add the IFF in the middle, or if and only if, the double arrow. Three different ways to denote it. Our original statement, P implies Q, we said was true. Our converse, Q implies P, we said was true. And that makes our biconditional statement, a closed figure has three sides, if and only if it is a triangle, also true. A good definition must be two things. Number one, you must be able to reverse it. And number two, all of the terms in the definition must be clearly defined. Okay, so we're looking for defined terms, reversible. If we have both those conditions met, then we have what is called a good definition. All right, for example, The following good or bad definitions. Rectangles, and definition will be figures with 4 corners. What do you think? Would that be a good definition for a rectangle? It's a figure with 4 corners. I would say no. I hope you said no as well. First of all, is it reversible? A figure with 4 corners is not necessarily a rectangle. That could be a square. So it's not reversible. This is a bad definition. Okay, furthermore, are all the terms clearly defined? Well, corners is tricky. You might read corners and think, okay, a 90-degree angle, but corner is not necessarily defined as a 90-degree angle. So again, supporting that would be a bad definition for a rectangle. A penny is a coin worth 1 cent. What do you think? Would that be a good definition for a penny? A coin worth 1 cent. Check if it's reversible. Is a coin worth 1 cent? Is that a penny? Are all of those terms clearly defined? And the answer is yes to both of those. That is reversible. A coin worth 1 cent is a penny. And all of the terms in the definition are clearly defined and precise. So that is what makes a good definition versus a bad definition. Now, we talked about inductive reasoning before, which was based on patterns, sometimes educated guesses, where we form a conclusion. Now we're going to talk about a different type of reasoning. It's called deductive reasoning. The process of proving a specific conclusion from one or more general statements. A conclusion that is proved true by deductive reasoning is called a theorem. So this is quite different than inductive reasoning. We're looking at a pattern. It could maybe go this way, maybe that way. Odds are went a certain way, but this is totally different. This is proving a specific conclusion. And if we can do that through deductive reasoning, we have what's called a theorem. So I have this nice figure here to do deductive versus inductive reasoning, just so you can see the two. In deductive reasoning, you start with theory, and then you form a hypothesis, make some observations, and then do your confirmation. So that's the deductive reasoning thought process. Inductive reasoning, you do not start with theory. You start with observations. Remember, we were observing the patterns? We were observing the patterns, and then we came up with a tentative hypothesis, so like what we thought the next 2 terms would be, and then we concluded with our theory. So that is the inductive thought process, okay? Deductive reasoning is when you start from things you assume to be true and draw conclusions that must be true if your assumptions are true. Let me try to explain that through example. All dogs have a tail. Do we assume this to be true? Okay, sure, let's assume that to be true. Buddy is a dog. Okay, so we need to make a conclusion, and it's going to be based on assuming this is true. There may be cases of dogs that don't have tails, whether it was at birth or later on in life, they lost it for some reason, but we're not looking at that. We're looking as if we are assuming this statement to be true, that all dogs have tails. Okay, so just like set it in your brain temporarily. This is a true statement. All dogs have tails. Once that's set in your brain, what do you think about Buddy? Buddy is a dog. Can you make a conclusion about his having a tail? And if that assumption is in fact true, then Buddy would have a tail. Okay. Is that necessarily true? No, but that's how deductive reasoning works. Whatever those first statements are, you assume those to be true. You move forward assuming them to be true, and then you make a conclusion based off of that. All right, we have 2 laws we're going to talk about. One is called the law of syllogism, and it is if P implies Q is true. So if your conditional statement has a true truth value, and Q implies R is true, oh, we have a new variable there, So P implies Q, Q implies R. And if both of those are true, then we can basically eliminate Q, and we can just jump straight to, well, then P would imply R, and that would also have a truth value of true. Let me see if I have it in. I'm going to write out for you like this. P implies Q, Q implies R. Then you can, I'm going to make like a conclusion line like in math. P implies R, like that. So you can just basically cancel out, skip over Q, because we know if P happens, Q is going to happen. And if we know if Q happens, R is going to happen. So might as well just say, well, if P is going to happen, then R is going to happen. All right, so there, that is in symbols for you. Here we have it in words. Use the law of syllogism to form a true conclusion. P implies R. So basically, you guys, they're asking us to cut out Q, cut out the middleman. If a figure is a square, then the figure is a rectangle. If a figure is a rectangle, then the figure has 4 sides. All right, so you find the common part, the Q. So this is P, this is Q, this is Q again, and this is R. So we cross out Q, and we go straight to, if a figure is a square, then the figure is a rectangle. Wait a second. Oh, I'm going to show the crossing out. Okay, breaking it down. P, Q, Q, R, crossing out the 2 blue ones, and now we have our result. P implies R, which would be true. If a figure is a square, then the figure has 4 sides. Good. Okay. And that will conclude. I thought we had a second law. We were going to talk about law of detachment. I might get back to you on the law of detachment. And that will conclude our discussion on Chapter 2. My name is Jami Emigh. Thank you for joining me, and I will see you next time for our discussion on Chapter 3.